Okay, so welcome to video 7. This will be the last video for the week. And what I want to do here is I'm going to cover, so these are the notes from the PDF that's was first uploaded with video 5. So section 3.1, 3.2. And I'm going to cover, so we did in the first 2 videos of the week, so video 4, video 5, video 6, we've done up to question 3. So I'm going to do examples 4, 5, and 6 now, which combine the chain rule with other derivative rules that we've learned, namely the product rule and a quotient rule. And so I'll start with number 4, then I'll do number 6, and then we'll talk about number 5 at the end. There's 2 ways to skin the cat there, and you can pick which one you like the best. So I'm going to go to the yellow pad again because it's easier for me to write more and it doesn't freeze as much. This is really unpleasant, and we can talk about figure out what to do next week. But hopefully this is okay. Okay, so in this video, we combine our newfound knowledge of the chain rule with other derivative rules that we've come to know and love, hopefully, namely the power rule and quotient rule, sorry, the product rule and quotient rule. Okay, so we start with example 4 from the sheet, from the note sheet PDF. Example 4, so it asks us to find y prime for the function y equals x cubed minus 7 over 6x, the root of 6x plus 12. Okay, now for this function, when I look at this and we want to play our little plug it into your calculator game, right? If you were computing, say, h at 2, or sorry, y at 2, I haven't given this a name. Y at 2, this would be 2 cubed minus 7 divided by, 6 times 2 plus 12. The last thing you would hit on your calculator is to divide the quantity q cubed minus 7 by the root of 6 times 2 plus 12. So the outermost operation is taking the quotient in some sense of these 2 functions. So we are going to first have to apply the quotient rule, and then to compute the derivative of the denominator that comes up in the quotient rule, we'll need to use the chain rule. So to find y prime, we will have to use the quotient rule followed by the chain rule. Okay, so first I will write y equals f at x over g at x, where f at x is x cubed minus 7, and g at x is the root of 6x plus 12. Okay, and so we first applying the quotient rule. So applying the quotient rule, we get f prime at x, sorry, y prime equals f prime at x, so the derivative of the numerator times the denominator minus the derivative of the denominator times the numerator all over the denominator squared, right? That's what the quotient rule says. Okay, Now, we need to find these derivatives, the derivative of the f and g, right? Where f is given here and the g is given here. Now, the derivative of f, we can just get from the power rule. So we put f up there. So it's just 3x squared, since the derivative of 7 is 0. But what about the derivative of g? Now, the derivative of g is the derivative of this root function. It's the root of 6x plus 12. Now, we recognize for this, we need the chain rule. So to compute this derivative, we need the chain rule. Now this we can kind of recognize it, so recognize that g at x is a composition. Now I can't use f because we've already used f, but I'll use like h and k of h and k at x, where the outermost function is the last operation that you would do to compute g, so which is take the square root. So where h at x is the square root function, and k at x is 6x plus 12. So by the chain rule, g prime at x is h prime evaluated at k at x times k prime at x, right? Now, the derivative of h by power rule is just the derivative of root x, which is the derivative of x to the 1/2, which is 1/2 x to the minus 1/2. Right? And the derivative of k is just the derivative of this line, so a line of slope 6. So the derivative of k is just 6. So that's pretty easy. So g prime at x is equal to 1/2 so it's 1/2 x to the minus 1/2 evaluated at k, evaluated at this line. So it's 1/2 6x plus 12 to the minus 1/2 times the derivative of k, which is 6, right? So that's what the chain rule says. Okay, so now we can simplify this. I guess we can simplify this a bit. So let's not rush to conclusions right now. So let's write g prime at x. So 1/2 times 6 is 3. So it's 3 times 6x plus 12 to the minus 1/2. So that gives a pretty easy expression, which we can write, if you like, g is 3 then over the root of 6x plus 12. Okie dokie. So we have our expression for g prime, and we have, where did it go? Way back up here, our expression for f prime. And now we got to take these two expressions and substitute them into the expression for y prime. So we substitute these, these expressions, the formula of these expressions, these expressions for f prime at x and g prime at x into the formula we obtained from the quotient rule. Which we just do here. Oops. Sometimes this paste function is very good. Okay, so let's see. So y prime then, so the derivative of f was 3x squared, g was the root of 6x plus 12, minus the derivative of g. You know, this is a little bit of a complicated gadget, so be careful with your parentheses, over 3 over the root of 6x plus 12, times f, which was x cubed minus 7, over the root of 6x plus 12 squared. Now, this looks rather ugly, but we can simplify it actually in a nice way. So it might be worth doing a little bit of simplification here. And so bear with me as we do some algebra. Okay, so we should try to simplify this a bit. So we get y prime, 3x squared, the root of 6x plus 12, minus, and let me put this x cubed minus 7 into the numerator here. So minus 3 times x cubed minus 7 divided by the root of 6x plus 12. All over. Okay, now if you square the square root, right, you just get 6x plus 12. And now what I'm going to do is I'm going to add these two rational expressions in the numerator by putting this guy, this 3x squared times the root of 6x plus 12 over a denominator of the root of the same quantity. Put it over a denominator of the root of 6x plus 12. And then when I do that, I can move this denominator down here. So, and add the numerators. So this is 3x squared times 6x plus 12 minus 3 times x cubed minus 7 divided by 6x plus 12 times the root of 6x plus 12. And now this, we can actually simplify this a bit. So we get y prime. So 3x squared times 6x is 18x cubed plus 36x squared minus 3x cubed plus 21. And that's divided by, now 6x plus 12 times the root of 6x plus 12. 6x plus 12 is 6x plus 12 to the 1. The root of 6x plus 12 is 6x plus 12 to the 1/2 power. So laws of exponents actually gives you 6x plus 12 to the 3/2. And now we can clean up the numerator and we get y prime is 15x cubed plus 36x squared plus 21 divided by 6x plus 12 to the 3/2. And yeah, I would leave it like that for now. There is some factoring you can do, but it's not going to be that pleasant, I think. So let's leave it like that. That's as simple as we'll get to. So I think now when you have these derivatives involving the chain rule and the quotient rule together, they do result in more complicated algebraic expressions than the previous one. So go over this carefully. You know, after this point, right? Like after this point, it's just all algebra from here. But it's algebra which you should be comfortable with. Because for the applications, you need to be able to simplify these. Okay, so I hope that's kind of okay. So now I want to skip to the last example on this sheet. So the example 6 on page 3. That's what I want to skip to. Okay, so now we're going to do example 6 on page 3. And this combines the product rule with the quotient rule. So, sorry, the product rule with the chain rule. Okay, so here's the example. So find the derivative ddx of x squared 2x plus 3 to the 7th power. Okay, so let's let h at x be this function x squared 2x plus 3 to the 7th power. Okay, so I first recognize that like the kind of outermost operation you're doing is multiplying the function f is x squared with the function g is 2 to the x plus 3 to the 7th power. So basically, if you were, again, doing this in your calculator, the last thing you would do is multiply the value of x squared with this ugly value of 2x plus 3 to the 7th. So the first derivative rule you apply, kind of working from backwards in a sense, is apply the product rule. And then we'll apply the chain rule to compute the derivative of g. So first, so let f at x equal x squared, oops, and g at x equal 2x plus 3 to the 7th power. And note that h at x is the product of f and g at x. So to compute h prime at x, we will first apply the power rule. Sorry, first apply the product rule. Followed by the chain rule, as you'll see. So recall, the product rule says that h prime at x is equal to derivative of the first factor times the second factor, plus first factor times derivative of second. So that's our happy product rule formula. All right, so let's take this apart then, okay? Let's do this, work this out. So maybe you should zoom out so we can see the h. So h prime at x is derivative of the first guy. So derivative of x squared times g plus, I'll go down this line, x squared times the derivative of g. Right, so the derivative of 2x plus 3 raised to the 7th power. Okay, now I'm going to be a bit fast about this because at some point, like writing out all these functions and the composition and computing all their different derivatives separately, at some point you should get good enough that you can kind of do this in your head. If you do enough of these examples, you kind of can internalize a chain rule, so you're able to do this in your head. So let me kind of show you how this would work. So the derivative of x squared is just 2x, so it just becomes 2x. And you get 2x plus 3 to the 7. Then you get plus x squared, now times the derivative of g. All right? Now I could write out, like what I did in the last several examples, is write out all this, write out this function as h composed with k and do all those derivatives. But if you do enough of these, you should be able to kind of get to the point where you visualize what the composition actually is in your head and you can just perform the chain rule. So here's how I'm going to do it. So we'll have the first term, okay, plus x squared. Now this function, which is what I call g at x, is 2x plus 3 to the 7th, is the composition of 2x plus 3 is the inner, and raised to the 7th power is the outer. So derivative of raised to the 7th power is 7 to the 6, but it's evaluated at the inner times the derivative of the inner times the derivative of 2x plus 3, right? So that's how I kind of do this in my head without writing it all out. So derivative of raised to the 7th is 7 to the 7 whatever to the 6, right? But it's 7x to the 6, but it's evaluated as the inner function. And then I just got times the derivative of the inner, which is derivative of 2x plus 3, and that's just 2. So this is 2x times 2x plus 3 to the 7th power plus x squared times 7 2x plus 3 to the 6th power times 2. And now you can simplify this a bit. You can actually do some nice common factoring here. So this is h prime at x is 2x times 2x plus 3 to the 7 plus 14x squared times 2x plus 3 to the 6. And now you can factor out, let me clean this up a bit. We can factor out a term of 2x plus 3 to the 6. And actually we can factor out not just 2x plus 3 to the 6, we have a common factor also of x. So x times 2x plus 3 to the 6. If you do that, you get h prime at x is x times 2x plus 3 to the 6th power times 2 times 2x plus 3 to the 1, right? So 7 minus 6 is 1, plus 14x. And so then h prime at x becomes x times 2x plus 3 to the 6 times 4x, so 2 times 2, x is 4x, plus 6 plus 14x. So you get h prime at x is x times 2x plus 3 to the 6th power, minus 18x plus 6. And if you want to be really fancy, you can factor a 6 out of this, and you get h prime at x is 6x, 2x plus 3 to 2x plus 3 to the 6 times 3x plus 1. And that is the answer in completely, fully factored form. And I mean, this last, again, like with the last example, this last part like isn't calculus per se, right? Once you get down to here, the calculus is done. And the calculus was actually done here, but you should combine 2 and 7 into 14. This is doing some algebra to get the answer as simple as possible. And for applications, that's really, really useful, as we'll see later in the course. Okay, so it's good practice to do this now, to refresh your algebra simplifications. Okay, so the last example is number 5 on the sheet. And I want to save this to the end. It's a little less complicated than the previous two, but there's different ways to do it. So the question is to find the slope of the tangent line. The slope, of the tangent line to the function f at x equals 2 over the root of x plus 3 when x is equal to 9. Okay, so you have, so, okay, what does it mean find the slope of the tangent line, right? The slope, remember, slope of the tangent line is the derivative evaluated at 9. The derivative is this function of slopes, which is giving you the slope at every point. So the slope of the tangent line at x equals 9 is just f prime at 9. So we need to find, oops. So we need to find f prime at x and evaluate it at 9. At x equals 9. Okay. So now there's two ways to find f prime. You can use the quotient rule, and if you use the quotient rule, you don't have to use the chain rule, or you can use the chain rule. So, because the quotient rule is messy and we're practicing the chain rule, let's do this using the chain rule. So in this case, there are two ways to find f prime at x. Method 1, recognize f at x as the quotient f at x equals g at x over h at x, where g at x, where g at x is 2, is the constant function 2, and h at x is the function, the root of x plus 3, and then apply the quotient rule. Rule to find f prime. Okay, in the second method, which we'll do today, use the chain rule by writing f as f at x equals 2 times the root of x plus 3 to the minus 1. And then f at x is g composed of h at x, where g at x is 2x to the minus 1. And the inner function h at x is the root of x plus 3. So that's what I'll do today. Because I don't know, I don't like using the quotient rule if possible. And we're practicing the chain rule, and this can be done quite nicely with the chain rule. If there had been a non-constant function in the numerator, like if this hadn't been a 2, say up here, if this hadn't been a 2 but like a 2x, then you'd have to use the quotient rule. I mean, yeah. So but in this case, we can get away with it. So by the chain rule, okay, the derivative of f is the derivative, right, is the derivative of this guy. Okay, so the outer function is 2 to the x minus 1. So the derivative of 2 to the x minus 1 by the power rule, the minus 1 comes down. It's exponentiate to the minus 2, evaluated at the inner function. Then times the derivative of the inner function. And so this is minus 2, the root of x plus 3 to the minus 2. And then this is by power rule. It's just 1/2 x to the minus 1/2. So this is f prime. From the chain rule. Now we need to evaluate this at x equals 9. Now f prime at 9 is given by minus 2, the root of 9 plus 3 to the minus 2, plus 1/2, 9 to the minus 1/2. So f prime at 9, okay, so root of 9 is 3, so this is 6 to the minus 2. So 1/2. Okay, 9 to the minus 1/2 is 1 over the root of 9. So we can write it like that. And we can do a little simplification, right? The 2 here will cancel with the 2 here. And then we can put 6 to the minus 2 is 1 over 36. So this is f prime at 9 is minus 1 over 36 times 1 over 3. So 36 times, so it's minus 1. 36 times 3 is 108. So the slope of the tangent line to f at x equals 9 is minus 1 over 108, which is what I would have guessed. No, just kidding. But so that's how you could do it using the chain rule. So maybe as a nice exercise, it might be a good exercise is to do this question using the quotient rule and check to see if you get the same answer. Right, because you should. The answer, like the slope of the tangent line, the value of the derivative should be independent of the way you calculate it, right? So either I made a mistake here if you get something different, or you make a mistake, or maybe we both agree, and if we both agree, then likelihood is this is correct, but it is correct as far as I can tell. Okay, so that concludes our discussion of the chain rule and the videos for this week. I'll enjoy seeing you in the live meetings, and thanks for tuning in.